So now we're on to our next topic, which is root finding for nonlinear equations, okay? So we wanna be able to use a method where we start knowing one guess, and then we can refine our guess to whatever it is that we're trying to solve. Okay, so with root finding for nonlinear equations, we're going to be using an iterative method. To solve f of x is equal to 0. So we're going to begin with a guess. We're going to call it x naught. And then we're going to find subsequent guesses to be something, some function of the guess before. All right. And so then we're going to end up with what we're going to have as a definition is this sequence xn, where n is greater than or equal to 0, is going to be a sequence of iterates. Now, as we keep finding xn, we are prayerfully hoping that xn looks like the one before, and then we can say eventually they all kind of look the same, so we're converging to something. All right, so here's another definition. A sequence of iterates xn, where n is greater than or equal to 0, is said to converge with order p greater than or equal to 1 if the following thing takes place. So if the absolute value of alpha, and this sequence of iterates is going to converge to alpha. So alpha minus xn plus 1 is less than or equal to c, that's some positive number, times the absolute value of alpha minus xn to the p. All right, so we're looking at the error in the n plus first iterate, that's en plus 1. It has to be less than a constant times the error in the nth iterate raised to the p. And this is true for some c positive greater than 0. If p is equal to 1, the sequence is said to converge linearly to alpha. Okay. So that is the absolute value of alpha minus xn plus 1 is less than c times the absolute value of alpha minus xn, all right? Or just that en plus 1 is less than c, less than or equal to c times en. And in this case, we require c to be less than 1. So 0. Okay. And the constant C is called the rate of linear convergence of xn to alpha. Okay, so let's do our first method. First method is one that these are going to seem familiar to you. So the first one is the bisection method. It's actually a rather slow converging method. Okay. So we want to solve f of x is equal to 0 on some interval AB. All right. So we're going to assume that f of x is continuous on the interval AB, and without loss of generality, we're going to assume that f of A is less than f of B. Okay. No, that's not what I want. I could assume that. Let's just assume that f of A times f of B is negative. So one of them is positive and one of them is negative. Okay. By the intermediate value theorem, there has to exist a C inside the interval AB such that f of C is equal to 0. All right. So we know that f of x has a root inside the interval AB. Now, there's no point in trying to even do this algorithm if this is not true. Let's start. So that's why we need that little bit of theory there. So I'm going to do without loss of generality. Okay. So here's A, here's B. I'm going to make f of A down here and f of B up here. So without loss of generality, it looks like this. So I have a root. Okay. So now the way we actually conduct this algorithm is we're going to start with the interval AB. And then we're going to bisect it and divide it into two and get two intervals now, AC and CB. So if I divided this interval into two, it might be somewhere right about here. And when I do that, I see that my root is between A and C. So therefore, I'm going to now let C be equal to B, let B equal to C. So I'm going to redefine B. So here we're going to let B now be C, where C was A plus B over 2. So I divided the interval in 2, found C, and then I'll check again to see if f of A and f of B is negative. If f of A and f of C are both the same different sign, then I know it's in that interval. If f of C and f of B are both this are of opposite sign, I should have said it right. If f of A and f of C are opposite sign, I know it's in AC. If f of C and f of B are opposite signs, I know it's in CB. So once I know what interval it is, I'm either going to let B equal C or I'm going to let A equal C. And so now I'm going to do it again. So now I'm going to chop it in half again and get a new C. So now I'm going to get a new C. And this time I find out that my root is between C and B. So now I'm going to let A be C. And I will keep doing this until eventually the distance between A and B and C are almost the same. They're almost the same number. So I have to figure out a predetermined guess of how close I want this to be, because with numerics, it'll never be 0, but I have to try to figure out exactly how small I want it to be. Okay. So here's my algorithm. Okay. So this is guaranteed by the intermediate value theorem to find the root. So I don't have to worry that this is not going to find the root, because I know it is, because it's guaranteed. Okay. So my A and B are given. All right. If A and B are not given, you need to come up with an A and B to give you a guess of where you think it might be between. Okay. So the first thing I'm going to do is choose A and B if they're not given. Okay. Such that when I take f of A and multiply it by f of B, I get a negative number. I also need to choose an epsilon tolerance. Now, again, the smaller epsilon is, the more accurate my solution will be, but the smaller epsilon is, the longer my code will run. So we might make epsilon equal to 1 times 10 to the minus 5. That's really, really small. Okay, I probably wouldn't make it like 10 to the minus 10. And this can actually change. So why don't I just make this 10 to the minus K. And then K is variable. Okay. So then after I do that, I need to let C equal A plus B divided by 2. So I find that midpoint. Number 3, if B minus C is less than or equal to epsilon, then my root is equal to C, and I need to exit the code, exit the algorithm. All right. Now, if B minus C is not less than epsilon, that means I'm not close enough to it. So now I'm going to take if the sign of B, the sign of f of B, times the sign of f of c is less than or equal to 0, then A is equal to C. Else, or otherwise, we'll let B equal to C. And then step 5, we need to return to step 2. Okay, so that's the algorithm. All right, so in general, we want to choose A, B to be a small interval. We don't want to pick something humongous because it will cause, we really would like to try to choose to graph our thing and then be able to select A and B to be something reasonably small, but not so small that we actually have allowed the calculator to do the algorithm for us. Okay, any questions about that algorithm? Do you see how it actually works? Hello?
I'm okay.
Okay. All righty. Not a hard algorithm. So let's look at the rate of convergence. All righty. So first thing is En. We already know is the absolute value of alpha minus xn. And that is the error in the approximation xn. Okay, so let's compute E1. So E1 is the absolute value of alpha minus x1. And I definitely know that that is less than or equal to b minus a over 2, because that's the distance between alpha and x1 can't be any bigger than half the interval, because it has to be on one side or the other. So E2 is going to be the absolute value of alpha minus x2. All right. So that has to be less than or equal to b minus a over 4. But that is b minus a over 2 squared. E3 is the absolute value of alpha minus x3. But now I've chopped up my interval so small that I know that my root is within an interval that is only the size of b minus a over 8. So this is b minus a over 2 cubed. So as you can see, we can start to develop a pattern here. I have 3, 3, 3. So once I start to see my pattern, I could say that En is the absolute value of alpha minus xn, and that's less than or equal to b minus a over 2 to the n. And I can do the same thing with En plus 1. It's the absolute value of alpha minus xn plus 1. And that's less than or equal to b minus a over 2 to the n plus 1. But I'm going to pull a 1/2 out of there and write this as b minus a over 2 to the n. So we get that En plus 1 is less than or equal to 1/2 En. So that implies P is equal to 1, which is linear convergence, and C is equal to 1/2. So the bisection method converges linearly with a rate of c equal to a half. And another way of saying this is the average rate of decrease of the error is equal to a half. Okay. So let's look at the rate of we want to look at the rate of decrease of the error. So let's find or consider the rate of decrease of the relative error. Okay, so we know that the relative error in xn is equal to alpha minus xn over alpha. So it's the true value minus the approximated value over the true value. All right, but that's approximately xn plus 1 minus xn over xn plus 1. All right, so therefore the rate of decrease of relative error is equal to the relative error in xn plus 1 divided by the relative error in xn. Okay. So now let's look into the advantages of this method. Okay, so the advantage of the first number one advantage is it is guaranteed to converge because of the intermediate value theorem. So that's first. And a reasonable error bound is available. Okay, so those are the two major advantages. Okay, what is the disadvantages? Well, the number one is that this thing converges slowly. So convergence is slow. So that's first. Number two, or B, it does not take into account the limits of the machine precision. Okay. So if A and B are really small, then when you choose B minus C, it may already be less than epsilon if if it starts off too close. So we have to be careful in that. Okay, so that takes care of the bisection method. Nice, simple, easy, done. Just keep bisecting the interval in half, and eventually you will come up on the root. Okay. Newton's method. Now you learn Newton's method in calculus 1. No, you learned it in calc 1 or calc 2. I'm trying to remember. Where did I teach Newton's method? I'm trying to remember. Okay. All right, so Newton's method is based on using the tangent and the tangent line to help us find a new root. Okay, so let's draw a picture of Newton's method. So here's Newton's method. Here's my function. And as you can see, there is a root right here. And I'm trying to eyeball my graph or whatever it is. And I say, you know, I'm not really sure what that value is, but I'm going to guess that that number is right here. So I guess X naught. So X naught is my initial guess again. All right, so now what I want to do is I need to go up to X naught on the function, find f of X naught right here, find the tangent line to the curve at that point. And then I'm going to ride out the tangent line till I bump into the x-axis, and I'm going to consider that to be my next guess, x1. But as I check, f of x1 is not 0. So I'm going to go back up to my curve. Here's f of x1. And then I'm going to find the tangent line to that. And again, I'm going to ride out through the tangent. And I bump into this point, x2. And again, I find that f of x2 is still not 0. So once again, I'm going to go up and find a tangent line so I can ride out through the tangent. And now I have a new point, x3. So now I started at x naught, then I got x1, and now I got x2. I want to keep following this until hopefully I get to some number xn, such that when I do f of xn, I actually get 0. Now, we already know that we can't see if f of xn is actually equal to 0. So instead, we'll look at the absolute value of f of xn to be less than some number epsilon we choose to be small. Okay, so here's what we get. So we start with x naught. And then we check because we're trying to find alpha. So this right here, again, this is our alpha. That's the one we're looking for. All right, so let's compute f prime at x naught. Well, it's the change in y over the change in x. And I'm being very hopeful where I have f of x naught minus 0 is I'm being very hopeful that my x1, f of x1 is 0. So here I'm hopeful that f of x1 is actually 0. Okay. So therefore now I get x naught minus x1 times f prime at x naught turns out to be f of x naught. So now when I multiply and solve, I actually will find out that the next iterate, x1, turns out to be x naught minus f of x1, I'm sorry, f of x naught divided by f prime of x naught. Now, there are a couple of things here that you should be saying, oh, wow, okay, anytime we divide by something, we have to worry about it. So in general, I can do the same thing with x2, being hopeful that f of x2 will actually also give me 0 as well. So as I keep doing this, I get a general formula. That is that x of xn plus 1 is going to take the one before, subtract off f of xn, and divide by f prime of xn. I know you guys have seen this before. You may not have coded it, but you definitely have seen it. Okay, so this right here is Newton's method. All right. You can alternatively derive it using Taylor's series as well. Okay. And either way, you still end up with that formula. Okay. So you have f of xn plus 1 is equal to f at xn plus f prime at xn times xn plus 1 minus xn plus f double prime at some cn over 2 factorial times xn plus 1 minus xn squared. So this term is the error. All right, and this is true when C is between xn and xn plus 1. So therefore, let's truncate it. So we're going to get f of xn plus 1 is equal to f of xn plus f prime of xn times xn plus 1 minus xn. And again, here's our hopefulness. Okay, so we're hopeful that that next one that f of xn plus 1 is 0. So now you get 0 is equal to f of xn plus f prime of xn. And this should be approximate. Times xn plus 1 minus xn. And if we're going to take that as our formula, we end up getting xn plus 1 is approximately xn minus f of xn over f prime at xn. Okay, so can anybody tell me, we haven't gotten to disadvantages and advantages yet, but can just looking at the formula, can anybody tell me where this will go haywire? How could this give me a problem when I code it? Okay, if we look at both formulas, they're the same formula, it doesn't matter. But here's the problem. This method will fail if f prime of xn is equal to 0 for any n. So if you get an iterate and the derivative is equal to 0, you're done. It doesn't work. Okay. All right, so let's do the algorithm. Okay. So the first thing we're going to do is we're going to have a value that we're going to call iterate. Okay. So we're going to set or define something called iterate. I usually call it iter equal to 1. So that tells you the number of iterates. And I also need to define an initial guess, X naught. And I also need to define an epsilon tolerance. And then we need to have an iteration max that says, you know what, after 200 iterations, just stop. You haven't gotten there yet. I don't know if you're going to converge, just stop, because it doesn't always converge. So this is the maximum number of iterations allowed. Okay. So now that we've gotten that, number 2, we need to actually calculate or compute f prime of x naught. Okay. All righty. I really hate to stop in the middle of this algorithm, but it is 1:15, and I don't want to keep you over. So I will stop here. Let me just say, if f prime of x naught is actually equal to 0, you need to exit. So numerically, you would say if the absolute value of f prime of x naught is less than epsilon, then you exit. And this might be a different epsilon. So let's make it epsilon 1. Okay. So that might be some different epsilon. Okay, so we will pick up here on Tuesday. I have uploaded another assignment, and I just got you guys assignments a little late, so I'll get those graded probably between today and tomorrow, and we'll keep moving along. You will have a computer project soon where you're going to be coding Newton's method and the bisection method and a couple other methods to be able to solve for roots of a polynomial, and actually an application problem. So start thinking about that. I'll be uploading that soon. So start thinking about your algorithms.